Lesson 90, Energy Examples. Example 1. How much energy is required for an 80-kilogram man to climb up a 4.0-meter staircase? Here's a very tall man climbing a 4-meter staircase. We can answer this question by determining how much stored or potential energy the man gains as he climbs the stairs. This would be equivalent to the amount of energy the man needs to use to climb the stairs. Potential energy equals mass times gravity times height. Potential energy equals 80 times 9.8 times 4. Potential energy is 3,140 Newton meters, or equally 3,140 joules. This coincidentally is the amount of work the man does to climb the stairs, which is now potential energy that the man gains and that can be used to come down off the stairs. Example number 2. How high can an 80-kilogram person climb after eating a Mars bar? Well, a Mars bar has about 238 calories. 1 calorie is equal to 4,200 joules. So 238 calories is roughly 1 million joules of energy. If we use the energy in the chocolate bar to climb up a hill, then that 1 million joules of energy will be converted to potential energy. Potential energy equals mgh. 1 million equals 80 times 9.8 times height. Isolating for height, we have 1 million divided by 80 times 9.8. Height is 1,275.5 meters, or 1,300 meters. That's quite the height up a mountain. Example number 3. What is the kinetic energy of a 5-gram bullet traveling at 700 meters per second? Kinetic energy equals 1/2 mv squared. E sub k is 0.005 times 700 squared. The kinetic energy of this bullet is 1,225 joules. Example number 4. What is the kinetic energy of a 2,000-kilogram car traveling at 3.5 meters per second, or roughly 12.6 kilometers per hour? Again, kinetic energy is 1/2 mv squared. E sub k is 1/2 2,000 times 3.5 squared. Kinetic energy is 12,250 joules. That's about 10 times that of the bullet. Well, which one should you be more worried about? The fast-moving bullet or the slow-moving car? The fast-moving bullet acts on a very small area, so there is a concentration of energy on a small space. I would worry about the bullet. How much energy is required to accelerate a 40-kilogram object from a velocity of 0 to 10 meters per second? The change in kinetic energy of the object would be the amount of energy that we would need to put into the object to accelerate it. So, change in kinetic energy equals final kinetic energy minus initial kinetic energy. Kinetic energy is 1/2 mv squared. Factor out 1/2 mass and we get 1/2 mass times vf squared minus vi squared. Since initial velocity is 0, we now have delta E sub k equals 1/2 mass times final velocity squared, which is 1/2 40 times 10 squared. The gain of kinetic energy, and therefore the amount of energy required to put into the object to accelerate it, is 2,000 joules. Example number 6. How much energy is required to accelerate the same 40-kilogram object from a velocity of 10 meters per second to 20 meters per second? While using our equation from example 5, we have change in kinetic energy equals 1/2 mass times final velocity squared minus initial velocity squared. Change in kinetic energy is 1/2 40 times 20 squared minus 10 squared. Delta E sub k is 1/2 40 times 400 minus 100. The gain of kinetic energy, and so the energy required to put into the accelerating object, is 6,000 joules. In both example number 5 and 6, we changed the velocity by 10 meters per second, but it took much more energy to change it from 10 meters to 20 meters per second than it was to change it from 0 to 10 meters per second. This shows us that gaining speed is difficult and requires more and more energy for equal gains in speed.